Welcome back, chemists. In this video, we will get into one of my favorite branches of chemistry, known as organic chemistry. And so this unit is going to build on what you've already learned about bonding, specifically covalent bonding. And we're going to be talking about valence bond theory today. So after this video, you should be able to describe the main features of valence bond theory. Recognize the premise for valence bond theory is that bonding results from an overlap of atomic orbitals, and distinguish how sigma and pi bonds are formed. And then finally, identify the molecular and electron pair geometry for a given molecule. So that's good because that's a little bit of review. So valence bond theory has the abbreviation VBT. And basically what we say is that an orbital is a region of space in which there's a high probability of finding an electron. You probably learned about that if you were talking about light and learning about Heisenberg's uncertainty principle and looking at the quantum mechanical model of the atom. So all you need to know is that an orbital is just an area of space where we're most likely to find an electron. Now, valence bond theory stems from the fact that we can take these orbitals and overlap them. And that is what results in a bond. So a bond is really just an overlapping of these orbitals that are made from these areas of high probability of locating the electron. The main points of valence bond theory are very simple. First, it says that orbitals have to overlap to form a bond between two atoms. Two electrons of opposite spins can be accommodated in the overlapping orbitals, and you may recognize this from Pauli's principle in talking about how electrons must have opposite spins. And then finally, bonding electrons have a higher probability of being found in between the two nuclei. The electrons are simultaneously attracted to both nuclei in the bond. There are two major types of bonds that we use to describe the bonding in molecules. And so the first is the sigma bond. So that's the Greek letter symbol for sigma. And this is a bond formed by the overlap of orbitals, specifically head to head. And I'm going to show you a pictorial representation of what this looks like. And so the bonding of the electron density is concentrated along the axis of the bond. And then the pi bond is the other type. So it has the symbol pi, and this is where the second and third bond in a multi-bond is going to be a pi bond. And this results in the overlap above and below the plane, sideways of the p orbitals. So let me show you examples of what these look like. So here are some examples of sigma bonds. So you could take an s orbital and an s orbital and overlap them. And again, what's concentrated in the middle in that blue area, that's the sigma bond. You could also form a sigma bond by overlapping an s orbital and a p orbital. And then you can form a sigma bond by overlapping p orbitals, what we call head to head, so that those blue regions represent all of those sigma bonds. Here are some examples with actual molecules in chemistry. So something like a hydrogen, when a hydrogen molecule, when you have two atoms of hydrogen combine, right, each of those electrons are going to combine such that they have opposite spins, and it's that overlap that creates your H2 molecule. And the nuclei of each hydrogen atom attracts those electrons. You could also have the hydrogen chloride molecule, where the hydrogen overlaps with one of the p orbitals. And so we'll see that the HCl will again form a sigma bond, that single bond between the H and the Cl. And then finally, we can see another sigma bond example where we are forming the F2 molecule, the fluorine molecule, where again we have two F atoms where their orbitals will overlap with opposite spins, just like you see there. So those are all examples of how sigma bonds form. Now we'll move into how pi bonds and sigma bonds compare to each other. So a pi bond is different in that we will see overlap not head to head, but instead above and below the plane, as we say. So where you see those dotted lines, that would be like, for example, the nuclei of the two atoms, and you see the pi bonds form above and below it. And so this would what we call sideways overlap. That's your pi bond. So in order for this to happen, notice how the p orbitals have to be parallel to each other, right? They have to be straight up and down. Whereas if we look at sigma bonds, again, we see the overlap head to head. And so you can see it's in the same plane, so we call it head-on overlap, and so that is your sigma bond. Notice that pi bonds and sigma bonds, again, the overlap is different, and in p orbitals, those are the only ones that can do both. The s orbitals are only capable of doing sigma bonds. So this is a video that I'm going to link in the description, and I'm going to suggest that you definitely watch this, but try not to get too hung up on the terminology here, because some of this terminology you haven't heard before, but we are going to revisit this video later on, and you will be hearing this video. But I want you to focus on in this video looking at the way the orbitals are overlapping so that you can understand what I mean when I say overlap head to head and above and below the plane. So make sure you take a look at this video, and like I said, I'll link it in the description for you. So now let's talk about the way that we can describe geometry of a molecule. You're already familiar with molecular geometry. So now we're going to extend this a little bit further and talk about something called electron pair geometry. So electron pair geometry is the geometry taken up by all the valence electron pairs around the central atom. This is regardless of whether they are bonded pairs or lone pairs. They're treated exactly the same. Whereas you've already been familiar with molecular geometry, which is just describing the geometry of the bonded atoms specifically. So we're only looking at the geometry of that central atom with the bonded atoms to it. So for example, here's ammonia, right? When we look at ammonia, this is what it looks like, and there's an unshared pair of electrons on the top there. That's what makes this a pyramid shape. So the molecular geometry is pyramid, which you're familiar with because, again, all those atoms are kind of pushed downward. It looks like a pyramid. However, the electron pair geometry treats all the bonded atoms and electron pairs identically. So that means that we say that this is technically a tetrahedral electron pair geometry. So since it has 4 electron domains, we say that it's tetrahedral. Here's water. So this is the water molecule. We say that it's bent because it has 2 unshared pairs of electrons. Again, though, it has 4 electron domains. So we say that the electron pair geometry is tetrahedral again. And so this is something that, again, you'll have an opportunity to practice with and focus on which types of orbitals are going to be overlapping for the different bond types. Thank you so much for watching. You can start worksheet 1H.